Recording. All right, so welcome everybody. This is exciting. So as I think everyone online knows, the first in what's going to be a quarterly series of cross-urban IFL seminar presentations on critical topics that are relevant to all of our projects. And so every 3 months, we're going to get together on one of these topics. And the way we've set this up is that we're always going to have two presenters from two different urban IFLs give their perspectives on the topic, followed by discussion. And so this particular month, the kickoff, we're doing the IFL approaches to climate scenarios, which I know all of us are thinking about a lot. And we've got a couple people who have thought about this deeply and have some great perspectives on it. And with that, I think I'll just hand it over to Paula to introduce the speakers.
Yeah, thanks, Ben. And yeah, good morning or good afternoon, I guess. Good morning, everyone. It's really great to see all this interest. So we have two talks lined up, and the first one is going to be Dr. Matei Georgescu. And so Matt is the director of Arizona State University Urban Climate Research Center in the School of Geographical Sciences and Urban Planning at ASU. And so he focuses on urban environment interactions, and in particular in improving the understanding and the characterization of distinct phenomena that are related to urbanization-induced landscape change. So there's a lot of focus on hydroclimatic and air quality impacts that result from large-scale urbanization, as well as potential adaptation and mitigation strategies. And so the work focuses really on environmental consequences, for example, on climate and hydrology, of also renewable energy expansion, by integrating really all elements of physical, agricultural, and social economic disciplines, in a sense, and fields. And so the range of tools that Matt uses include climate models, remote sensing data, and associated applications, and also in situ weather and climate observations. And with that, Matt, I'll pass it to you. So for the audience, we decided we're going to have the two talks first. So it's going to be like about 25 minutes, 30 minutes for each talk. At the end of each talk, if you really have a burning, clarifying question that you can't live without, please ask. Otherwise, we'll just let the two talks finish and then have a discussion session that is combining the two talks so that we can really, help favor the collaboration among all the labs. Matt, I'll pass it over to you.
Thank you, Paula. Can everybody hear me well? Okay, wonderful.
Sound good.
I'm going to press the share screen button here. And I trust that everybody can see my slides. Okay, so thank you for the introduction, Paula. Thank you, PI teams for providing this opportunity, not just for me, but for everybody. I think it's fantastic. Really share approaches and share ideas, novel approaches as we move forward in the really origin.
Matt, your mic is going a little bit in and out. So if you have a chance to be closer to the mic, that might be best, unless it was only on my side.
No, I was going to say the same thing. I don't know if it's you or someone else's background noise, but
yeah, maybe a little bit closer. It was in and out, so I think it's a matter of just being a little bit closer.
Okay, all right. I'll try to raise my voice a little bit just to make sure
that sounds great. That sounds great. Stay where you are.
I won't move at all. All right. So let us begin. As we're well aware, urban environments differ from their rural counterparts in large part because of their modification of incoming and outgoing energy. So the three main ways in which this is manifest is due to a modification of landscape features, land cover, land use characteristics. Second of them is due to the three-dimensional representation or morphological characteristics. Built environments are generally taller than their rural counterparts. And the third is due to the level of human activity, essentially how we use energy, air conditioning, lighting, transportation systems, how we get from location A to location B. We have to account for elements like thermal storage, account for this additional input of heat into the ambient environment, the modification of shortwave that is received at the surface, modification of long wave that is output to the clear sky. It's of course reduced. And so overall, these different processes result in a significant modulation of urban environments relative to their less developed or rural counterparts. And so these are, of course, all aspects of the urban environment that we have to include in our projections. And so for the past 10 to 15 years or so of my career, what I've been focused on is to try to, like Paula already indicated, improve understanding of these large scale, small scale to large scale on the scale of continents, distinct phenomena related to urban induced expansion and associated impacts as well. And so one of the key questions that I've had, which has, of course, led us eventually to the point in time that we find ourselves here, is to try to compare these two forcing agents. So all of the physical aspects that I've just talked about, which are biophysical characteristics of urban environments, the urban-induced climate change relative to climate change that occurs on the scale of cities due to greenhouse gas emissions. Okay, so these are two wholly separate and distinct forcing factors, but together in tandem, they work to modify urban environments. And so one of the principal questions that I've had is, what is the interplay among these forcing agents across urban agglomerations? And so I'm going to spend, I would say, about 2/3 of my talk trying to answer this question and convince you in a quantitative manner that the urban-induced signal is very important and how this has led to where we are today in terms of our SW-IFL project. So our first attempt to try to answer this question was through a series of simulations. This is going back to 2013 or so with colleagues here at ASU, Mohammed Mustawi, who is on the SW-IFL, and colleagues at NCAR. And we used a suite of ensemble-based WRF simulations with a contemporary landscape and urban representation, and a suite of future projections of Arizona's landscape. This initial study was Arizona-centric. And we asked a very simple question: what is the change in temperature, for example, or change in precipitation, or any other process-related variable? These are endpoint variables due to this change in urban representation. So what is the urban signal, for example? And we compare these results with completely distinct simulation output from global climate model data. At that time, global climate models were not incorporating into their suite of IPCC and the IPCC suite of simulations. They were not incorporating urban expansion. They still are not, actually. And we compared that output with GCM output by the middle of the century to try to get to the GHG signal. In this case, we were using IPCC, so this is CMIP3 output at the time. And so our focus here was really simple: try to make a comparison between 1 and 2. What's the urban signal? What's the greenhouse gas induced signal? Again, our focus was Arizona, so we conducted a set of simulations, a control, that's our baseline, maximum expansion, a minimum expansion, and then independent from this were the greenhouse gas simulations that did not include urban expansion. So what do some of these results, which served as the first direct quantitative assessment of urban to greenhouse gas induced climate effects, what do some of these results look like? Well, what I'm showing you here are, again, summertime through mid-century ratios of the urban signal on the numerator and the greenhouse gas induced signal on the denominator. You might be taking a little bit back when you see B1 scenario and A2 scenario. We're going back in time here. So this is 2013. So this is CMIP3 output. And essentially what we're indicating here, wherever you see reds and yellows, if we're focused on panel A, that indicates that the urban induced signal, so a maximum urban expansion. This was data obtained by our from Maricopa Association of Governments, so a local entity that is focused on sustainable development for the state of Arizona, according to a maximum urban expansion scenario divided by the minimum constraint due to greenhouse gas emissions, or a reduced emission scenario. We find that the urban signal is at least as important, averaged over the entire summer, as the greenhouse gas induced signal. If we incorporate, this is now panel B, adaptation scenario. In this case, it was just incorporation of highly reflective roofs. We see that all of those reds essentially over the state of Arizona turned to greens. Nevertheless, we still see an urban-induced signal. It's not negligible, and then a reduced, this is panel C, urban expansion relative to a maximum or aggressive greenhouse gas emission scenario. This leads once again to reduced urban signal, but not negligible urban signal. So again, urban-induced climate change, not negligible, regardless of the pathway of greenhouse gas emission scenario, and regardless actually of the pathway of urbanization as well. It's something that cannot be ignored. And that was the first statement in a quantitative sense that said, look, when we're talking about cities and future environmental change over cities, yes, greenhouse gas emissions are important, but how we build those cities is also important. And so our next step was to scale back, zoom out for the continental United States and perform a similar assessment for the entire continental United States. Here we looked at the end of the century. And again, it's using CMIP-3 GCM output. So we run our WRF simulations, and independent from this, we look at the GCM output scaled down to the individual cities, individual areas where urbanization is occurring. And I'm not going to go into each one of these panels, but the take-home message is that even in the lowest sense, a 20 to 30% urban-induced signal relative to the greenhouse gas-induced signal clearly indicates the importance of how we built these cities and the physical aspects that we introduced this talk with regarding input of solar radiation, the reduction in long-wave emission, the addition of anthropogenic heating, and so on and so forth. This was a consistent result for all of the major urbanizing areas across the United States, including Arizona and California and Texas. And it really reiterated what we had said previously, that the urban to greenhouse gas induced signal in terms of thermal impacts during the summertime are of a similar order of magnitude and really cannot be omitted. So we step forward a few years now and we say, well, there's a few things that we can improve upon. For example, conducting our WRF simulations independent of the global climate models. Maybe we can improve upon that, and we did. And so the next approach incorporated global climate model data directly into our WRF climate model simulations, where we initialized for future scenarios WRF and forced WRF at the lateral boundaries with two distinct global climate models that have different sensitivities to greenhouse gas forcing. These climate models were the CESM, this is the NCAR model, and the GFDL, the Geophysical Fluid Dynamics model out in New Jersey. And so what we're looking at is summertime differences, 10-year differences between end of century, so 2090 to 2100 minus 2000 to 2010. On the left-hand side is average, summertime average during the daytime. And on the right-hand side is summertime average during the nighttime. And again, we're contrasting the CSM model versus the GFDL model here, both with similar pathways of greenhouse gas emissions. If we look at the top left panel, we see these pink colors indicative of generally warming due to both greenhouse gas-induced climate change and urban expansion of about 5 to 6 Kelvin. These are the units that we're using here, Kelvin, and somewhat reduced warming in the Sunbelt areas. For the GFDL model during the daytime, we see warming maximized at about 3 to 4 Kelvin. So clearly a difference between the signal being imparted by WRF forced by the CSM model versus the GFDL model. During the nighttime, warming is considerably greater. We're getting up to about 8K in the northern, in the higher latitude urban areas in the United States with the CSM model, and less warming, but still pretty significant, 4, 5, 6K for the GFDL model. So considerable variability between these two forcing GCMs. So again, as a reminder, we're using these GCMs to force our WRF simulations, but summertime warming due to both urban expansion and greenhouse gas-induced climate change is quite significant for future US cities. One of the great things about these simulations that we conducted was, yes, they're 10-year simulations, but we produce data every 3 hours. So that allows us to assess impacts at the diurnal scale as well. And so that's what I'm showing you here on the x-axis. It's the diurnal scale. It's an average diurnal scale for the summertime. The top left is the CSM model, but with a reduced emission scenario. This is RCP 4.5. Directly below is the more aggressive RCP 8.5 scenario. And on the right-hand side, it's the GFDL model with an RCP with a more aggressive RCP 8.5 scenario. And the contours each delineate urban environments that correspond to specific national climate assessment regions. So for example, blue line indicates all urban areas in the Northwest and so on and so forth. And there's some similarity, but there are some differences among the different urban areas across the different geographies. And what I'm showing you here is, as before, it's the urban signal relative to the greenhouse gas induced signal. We're focusing on temperature for the sake of this discussion. So let's look at the top left panel. This is CSM RCP 4.5. The urban signal is generally, it can be greater for some urban environments, for example, in the Southwest, somewhat less. Let's call it a 1-to-1 correspondence during the evening and nighttime hours. So urban as important as the greenhouse gas induced climate signal, but of reduced importance during the daytime. Clearly, the greenhouse gas signal dominates during the daytime hours. If we ratchet up the greenhouse gas emission scenario, so this is now RCP 8.5 for CSM, even in this case, with a much more aggressive warming, CSM is quite more sensitive to CO2 forcing. We still see that the urban induced signal is not negligible, right? 50% generally between the nighttime hours and the evening hours. And once again, this consistency of a reduced impact during the daytime. Now we contrast this with another RCP 8.5. This is the GFDL model. And we notice that the bottom right-hand panel looks very similar to the top left-hand panel. In other words, there are important differences to take into account, not just due to emissions pathway, the difference between RCP 4.5 and 8.5, but also differences due to the individual GCM that is forcing these simulations, these regional climate model simulations. So the key takeaway messages, there's two important points. The relative urban induced impact varies across the diurnal cycle. Again, we maintain our initial conclusion that the urban induced signal is very important, but it's dominant during the evening and nighttime, at least as important, and it's of reduced impact during the daytime. In addition, quantifying the uncertainty associated with the GCM driver itself is as important as quantifying uncertainty associated with RCP or emissions, greenhouse gas emissions pathway. So following this, we took the very next step. It's the same data that I've been talking about since we incorporated the WRF simulations being driven by different global climate models and different pathways of emissions. And so we said, how does this impact, how does this translate into actual exposure at the human scale for individual cities? And what we did here was we accounted for the effect due to climate change. This is the greenhouse gas signal that I've been mentioning all along. We included the effect of urban development. Again, this is part of our overlying message, is that if you're projecting environmental change over urban agglomerations, you cannot ignore the urban signal. It is just as important as the greenhouse gas induced signal. And we additionally incorporated population migration, so the flux of people from cities across the United States. This was data retrieved from EPA. And we developed a new metric, and that new metric relies on quantifying extremes for a particular city. For example, what's considered extreme in terms of summertime temperature over New York City is going to be different for Phoenix, right? So the definition of extreme heat thresholds are contextually and geographically dependent. And what we said was the following: if you have one person that experiences 1 hour of extreme temperature, and we define extreme temperature as the 99th percentile of the initial decade of our simulation, that person has experienced 1 person-hour of exposure. And using this methodology, we then were able to calculate the relative change in end of century, 2090 to 2100, compared to the initial decade of the initial century for a whole suite of cities across the United States. These are color-coded by individual climatic regions. Averaged over the continental United States, we see a 30-fold increase in population-weighted heat exposure by the end of the century. So if you aggregate across all of these cities. But of course, you probably don't want to do that because you see significant variability from city to city. So Austin, for example, a considerable increase in population-weighted heat exposure, in large part driven by the increased migration to Austin, right? Remember the three variables that are core elements of this equation. It's not sufficient just for temperature to increase, but you also need to have people there to experience that temperature. But not all cities are experiencing these increases in population-weighted heat exposure. For example, we look at the Pacific Northwest cities, Portland and Seattle, we see reduced increase over those regions. So the relative projected impact of future extreme heat exposure is quite variable from city to city, but is significant for if we're averaging across the continental United States cities. In fact, there's no single city that does not undergo an increase for the end of the century compared to the start of the century for what we're looking at here is a high emissions scenario. So RCP 8.5 using the CESM model. Most recently, we were able to publish a paper focused on, so this appeared in the inaugural issue of Nature Cities. We asked the question, okay, so we're looking at adaptation mostly and trying to see if we can offset future increases in warming and potential changes in heat exposure. But we also said, or we also asked, well, how can we compare adaptation to mitigation using our simulations? And again, it's the end of century minus the last decade of the century minus the first decade of the century. And the way we incorporated mitigation into our simulation results is, or framework, is to conduct a set of simulations for the last decade using RCP 8.5, and then a separate distinct set of simulations using RCP 4.5. The difference between the two accounts for this reduction in greenhouse gas emissions. And again, we were able to look at individual cities. On the x-axis, we're looking at avoided person hours due to adaptation. And on the y-axis, we're looking at avoided person hours due to mitigation or reduced emissions of greenhouse gases. And the blue cities that you see here are the results from the CESM model driving wharf, and the orange results from the GFDL model. And most of these cities fall directly on these lines, which essentially indicates that there's as much efficacy in avoiding person hours or reducing heat exposure due to adaptation as mitigation. But some of these cities fall way off the line, like Denver, for example, which shows a greater reduction in person hours resulting from mitigation than adaptation. It's way to the left here. Leading us to, for example, ask, why is that happening for Denver? Why is that happening for any cities? For example, Portland is another one of these cities, and there's a handful of more such cities, which shows a greater reduction in person hours resulting from adaptation than mitigation strategies. So this really paves the way for incorporating both of these forcing agents at local scale to try to understand the physical mechanisms responsible for them. So now we're going to take a step back. We're going to take a step back and revisit regional climate modeling history a little bit. And we're going to go back into the 1980s, which was essentially the dawn of the regional climate modeling era. And at that time, global climate models were used to characterize future global and regional climate change. And so by virtue of not having sufficient computational power, resources, so on and so forth, the grid mesh size for those simulations were at best on the order of about 500 kilometers. And in fact, the Western United States, from some of these papers in the late 1980s, the peak elevation over the Rockies was represented right over Salt Lake City. This is, of course, problematic. It leads to inappropriate simulations, characterization of uplift and downslope and precipitation and temperature and so on and so forth. And so in this initial paper in 1989, Dickinson et al. Used predecessor of WRF. It was at that time the MM4 mesoscale model version 4. MM1 dates back into the late 1970s. So by the late 1980s, we're now into the MM4 era. And they compared simulations between MM4 and a global climate model output. In this case, they forced MM4 with CCM1 output and produced much more sensible and realistic precipitation and temperature at the local to regional scale and over the Western United States. This was essentially the dawn of the regional climate modeling era. MM4 up until this time had been used for simulations on the order of a couple of days, but not longer than that. This first effort conducted simulations for an entire month. And at that time, 1 month was indicative of climate scale. So fast forward about a decade or so, and Filippo Giorgi and Linda Mearns led a special issue in JGR Atmospheres, a rich set of papers that focused on a number of topics that were intended to really focus improvements and continued work on a range of regional climate modeling activities associated with simulation length, what constitutes climate, for example. Associated with spin-up, how much spin-up does one need? And of course, the answer depends on the particular context and the type of simulation. On the model physics and the compatibility with lateral boundary conditions. For example, back then, they did the same as we're doing now. We're forcing our models with data produced from an independent model. And this incompatibility with the model physics themselves might translate into errors that we can't quite track. They're not tractable. Issues like domain extent and resolution and spectral nudging and other types of nudging and variable mesh resolution was introduced with maybe a few years before, but really was highlighted as an important step forward in this special issue. So now fast forward to where we are here as part of the SW-IFL, which is in many ways trying to take some of that foundational work to try to formulate a new paradigm of regional climate modeling, but urban environmental modeling more explicitly, where the typical process for regional climate modeling is more of a top-down approach where you account for the flow, so atmospheric motion and how that impacts the land surface. What we're doing here is accounting for surface-induced modification through emissions of CO2, particulate matter, or incorporation of anthropogenic heat from the building level, and how this manifests itself through agent-based modeling down to the individual level as well. So a lot of different aspects associated with the development of what we refer to as the model of models, which is a global all the way down to an individual representation to try to characterize all of these different facets of the urban environment and of the atmosphere in conjunction in a dynamic and interactive sense. Includes data simulation and incorporating realistic building morphology and a lot of other factors that I'm not going to go on in detail here, but I am going to spend a few minutes in trying to essentially introduce this new framework here, which is a global to regional scale new framework that is really foundational for our model of models development. So it's MPAS, which is the parent or global version of WRF, serving as initial and boundary conditions for WRF relative to the traditional approach. So what does that mean exactly? Well, you'll recall a few minutes ago, I mentioned the special issue in JGR as essentially introducing this variable resolution approach as potentially new paradigm in regional climate modeling, where we're using MPAS now as one of our two approaches to substantiate the potential improvement in utility of a global scale variable mesh model down to 20 kilometers for most of the United States to execute this model for however long we want to execute the simulation and have this data become initial conditions be formulated as initial conditions and lateral boundary conditions for a WRF simulation. So this is our WRF simulation parent grid. So it's the typical telescoping parent grid to intermediate grid down to our fine grid down to 2 kilometer, representing the entire state of Arizona. And we contrast this with the traditional approach using reanalysis data. In this case, it's widely accepted that UR5 reanalysis is the best that there is, and using the exact same domain. So we run 2 sets of simulations, one using initial conditions and lateral boundary conditions obtained by MPAS, which only requires initial conditions, nothing else. And those initial conditions are obtained from ERA5. And then the second set of simulations using ERA5 to continuously update the lateral boundaries for our WRF simulation. So let's look at some of these first results. We conducted 10-day simulations for the summer of 2020, June 2020. Up until this past summer, June 2020 had been our hottest on record, and then 23 just absolutely blew it away. In keeping with the color scheme that we presented earlier, MPAS WRF temperature is depicted in the red contour. ERA5 WRF, this is the traditional approach, is depicted in the blue contour, and the observations are indicated in black. The observations are multiple urban observational sites courtesy of the Arizona Meteorological Network, which is hosted and maintained by University of Arizona. So we look at the first diurnal cycle, and we can see here that MPAS WRF actually seems to do considerably better in simulating the extrema on the nighttime and daytime side. So we're pretty happy with the initial diurnal cycle. For the second diurnal cycle, again, considerable improvement in both the daytime and the nighttime. So we're good there with our framework, sort of planting the flag and establishing this new paradigm. Diurnal cycle 3, well, not much difference during the daytime, but considerable improvement during the nighttime. Diurnal cycle, more of the same. We then see a transition in days 5 and 6, and then a complete degradation in the MPAS WRF approach for day 7, 8, 9. And we only conducted 10-day simulations here, but this trend is likely expected to continue, keeping in mind that the MPAS WRF approach only includes MPAS lateral boundary conditions which have no assimilated data. That initially assimilated data has already been lost after the first few days. Hence, setting the groundwork for data assimilation, which is the point in our work that we're currently focused on. So I'm going to leave this here for references and further reading, but really highlight some of the points that I've hopefully convinced you of, which is number one, a quantitative significant impact of the urban-induced signal, the direct urban-induced signal, independent and separate from the greenhouse gas forcing signal on the scale of cities. Second of all, trying to develop this model framework incorporating MPAS as our initial and lateral boundary conditions relative to the initial framework, and paving the way for the next step in our approach, which is the incorporation of data assimilation, and saying a little bit about the entire MOM framework as not just a top-down, but also a bottom-up approach into improved urban environmental change. So I'm going to stop there, and I guess we'll hold off for questions.
Thanks, Matt. Yeah, perfect timing. Yeah, unless there's some quick clarifying questions. If anybody has anything really burning they need to ask now, otherwise we'll move forward. Okay. So Matt, yeah, let's just wait for the discussion combined, and thanks for presenting. So while Rao will start sharing screen, I'm gonna introduce Dr. Rao Kotamarthi. So the first seminar was from the SW-IFL, and now we're gonna go into CROCUS. So we're gonna move from Arizona to Chicago, and Dr. Kotamarthi is the science director for the Center for Climate Resilience and Decision Sciences. And he's also a senior scientist at the Environmental Science Division at Argonne National Lab. And his research interests are really on atmospheric chemistry, absorbing aerosols, regional and urban scale climate modeling, and wind resource characterization. He has led a team of scientists in developing climate projections suitable for addressing climate impacts, resilience, and adaptation challenges, both at local and regional scales, and also for their application, for example, to utilities serving power and telecommunication industries. He also recently authored a book that was published by Cambridge University Press, which is on downscaling techniques for high-resolution climate projections from global change to local impacts. And with that, Rao, I'm going to pass it to you.
Okay, thank you. So this is going to be quite different from the previous talk, and my emphasis is while we are doing a lot of modeling right now for the urban project, I would kind of focus on a larger scale here, the larger problem of why downscaling. So why do we want to downscale? So let's start at the beginning. So we immediately jumped into downscaling with this first talks. So the projected direct impacts of climate change range from perceived nuisances like to severe disruptions, like affecting water, wastewater system, energy supplies, ecosystem, agriculture operation, all kinds of things that pretty much our entire way we live will be affected by some way by climate change. So if you take an example, even if the average rainfall remains constant, a shift towards more intense rainfall requires additional capacity in stormwater systems to protect against flooding. So one of the focuses of our urban IFLs is kind of try to figure this out at the scales of an urban city. And if you can kind of first understand what these things are and maybe provide some ideas on mitigating these effects. Why do you want to downscale? So essentially, there is a fundamental mismatch of spatial and sometimes even temporal scale between the output of GCMs that tend to simulate climate at a relatively both spatial scales and the information typically needed for assessing impacts and determining adaptation measures for human and natural systems. This is by design. This is not that the GCMs have somehow failed. The GCMs are basically developed as an energy balance models. The whole goal of GCMs is to see what would happen if various carbon profiles in the atmosphere change, how the atmosphere responds. They were not designed to do urban climate to start with. Now we are passed on to this era of Earth system model, so there is more and more of the kind of impacts that we are interested in, the human aspects getting included in them. But initial designs of GCM was absolutely not for this purpose. But most applications require climate projections that are not generated by GCMs, but are also, but then you have to bias correct and downscale in some manner to make them useful. So that's the whole idea of downscaling. So how do you assess the impacts of climate change, right? I mean, either urban or local or infrastructure. There are three ways people have been doing this. One is called the possible maximum precipitation, or PMP. Essentially, the idea is that a theoretical possible, you have a storm system, you can actually calculate theoretically the greatest amount of precipitation a storm of given size can produce. Then you use that to calculate, for example, if you're a hydraulic engineer or making some decisions, how big my spillway should be. That is based on something like a PMP estimate. So this works well or decently well for certain things like precipitation, where maybe we have some known physical limitations. Even there are challenges, like if there's where the system comes from and how what feeds into the system and how long the system lasts actually change those numbers quite a bit. So this has become quite challenging for other climate variables. Second one is called the storyline approach, and it's also people call it pseudo global warming. The idea here is that you have at the smallest scale, at the atomic scale, let's say, you have a storm that came and hit New York in 1980. You take that and put it into a future climate and see what happens. So essentially, you're building a storyline. This is very beneficial because you know what happened when that storm hit New York, so you have a story. You have an effect, impacts, and all those things. Now you take it into the future and see what effects are. Now you can build on that storyline to see what other effects happens. The pseudo global warming is essentially a kind of a wholesale approach to that. It takes the regional climate model or downscale model for the current climate, changes the some of the variables in the model to a future climate and runs it for tens and hundreds of years. So the idea is to capture many of these things, not just one. And so useful for building these kinds of storylines and more, maybe even doing statistics on how they change as you go into the future. One of the key things with climate modeling and downscaling and any impacts assessment is that it is uncertain. The uncertainty is quite significant. So you have to have enough simulations so you can do some kind of statistics on that and get a grip on the uncertainty estimates that you're producing. The third method, which is we call downscaling, is basically taking a climate model and bringing it to an appropriate scale. There are two popular approaches. One is called statistical downscaling. The second one is called dynamic downscaling. The statistical downscaling needs historical climate data to a site to develop projections, and dynamic downscaling uses physics-based model like the one Matt showed right now. So the idea here is that this is useful for hazard projection for future climate conditions, such as temperature extremes, all the things that we are worried about, and I talked before. So what are the drawbacks? The statistical downscaling is limited to a few variables. You can only do temperature, precipitation, and a few other things I've not mentioned here. Dynamic downscaling is computationally expensive and limits the number of ensemble fridges for uncertainty estimation. That's a key problem. So you can do dynamic downscaling to very high resolution, but you may be able to run only 3 to 6 ensemble members. Whereas with the statistical downscaling, there are 40 IPCC models. You can run downscale all of them for all the scenarios that they have done, which is basically 2 scenarios. So you can get 80-member ensemble for mid-century, for example. But you have to realize that most of the climate models are actually derived from CESM, the ones that are used world over, so that the diversity in these models is not so large that it actually makes sense to average them over and get a single number or even calculate uncertainty of them. The uncertainty band will be mostly determined by models which are quite different, as I show next. So dynamic downscaling, as was described before, is basically taking something like what you see on A there to B. So B is actually only shows every third grid point. So we are trying to refine the models by up to factors of 100 sometimes and larger in terms of area. So you're going from 100 by 100 kilometer scale to a 10 by 10 kilometer scale, square cell, or 4 by 4 cell. So this involves typically 3 phases. One is you have historical observations, that you have, that you use to bias correction select GCM, or a 5, that is, we call it a historical simulation, the tree analysis fields, and then prepare an input field for the RCM. The second phase for that is that you do a whole bunch of sensitivity tests on the model, something like WRF. WRF has lots of options. So which is the best physics model, that physics option package that you want to use? What are the nudging parameters? So if you want to do some kind of data nudging. So the idea here is that you don't want the climate model, the downscale model, to drift too far away from your climate model, so you can nudge. We have done that, but right now we don't do any of the calculations. We do any nudging, mainly because it increases the cost quite a bit. But the other thing happens is that when you nudge, it kills the variability, especially in small grid cells, which is of great interest to us because that's where most of the urban impacts occur. And if they all collapse into a single value, then it's not very useful. So then you run the model and you archive the output. So at Argonne, we have been doing this for quite a while. We have 2 data products. I was asked this question, so kind of focus is on this. First one we call ADA V1, which is Argonne Dynamically Downscaled Data Archive. It has about 330 years of simulations with WRF, which was done almost 7-8 years ago. And it was based on IPCC AR4. And it uses NCEP reanalysis, which is a reanalysis data set for about 1980 to 2010, about 30 years of simulations to do the historical simulation. The idea of doing that is that we try to understand the bias in the WRF model when you use it in this mode. And then we downscaled CCSM4, GFDL, and HADGEM, each of them 10-year time slices for now, mid-century, late century for RCP 4.5, 8.5. So overall, and we also, as I said before, we also did nudge, no nudge, and also bias corrected, no bias corrected. Bias correction in input fields actually does not change model output much, except in some small locations, which may be important for some applications. But it adds a lot of cost to the calculation, so we dropped that too. So these calculations are all available. I will show you where you can get them later. And the CMIP-6, the one that we are doing right now, is at 4 kilometers. We call it convection permitting. And this is a huge domain, the domains are shown on the right of your screen. The 12 kilometers, the 4 kilometers is even bigger. It goes all the way down to Puerto Rico. And we are slowly building these calculations. We are probably about 50 to 55% on our way. Year of analysis from 2001 to 2020 at this very high resolution convection permitting scale is done. And we have just published the first paper, that is Akinsanola in 2024 in Scientific Reports. And then we are CSM2, we are kind of on our way to completing the mid-century calculations. HAGEM is also picking up speed as we go, and MPI is also started. So we are making progress on all these things. And the simulations are again 20 years now instead of 10 years before. And the case studies like the RCP, the emission scenarios are 4.5 and 8.5, we kind of keep it consistent with the before previous one. So this is the same thing. This is the same thing that I showed before. So why did we pick these models? This question always comes up. We generally, when we did the ADA version 1, we looked at climate sensitivity of model. What is a climate sensitivity? Essentially, if you think about a pre-industrial carbon amount of greenhouse gas in the atmosphere, which is around 280 ppm, and double that and run your model to a steady state, then you see how much did the temperature in the model change. It is called climate sensitivity of the model. Each model has a characteristic sensitivity, and it is a measure of how fast the model reacts to a change. So what happens is they fall over a large range. Typically, based on data measurements, there's a lot of controversy recently. This number should be falling around less than 4, 3.5 to 4. I think the IPCC, recent IPCC picked a number around 3.9, I think. Anyway, this is a different way of, for this particular study, we defined it in a different way. We just took the base case, which we call 2014 to 1995, and then we are looking at the change at the end of the century, 20 years, historic 20 years, and which model gives the biggest change. So we ranked all of them, all the models that we know participated in IPCC, and picked 3 models, one with a lower, I shouldn't call it a sensitivity, but lower response to the end of the century, one with kind of a middling change, and the one very high sensitive. The reason is that each of these models behave this way because the physics package in that model is different. We don't know which physics is correct in a sense. We kind of know which should be correct, but we did not want to leave this on the uncertainty in the models itself. We wanted to capture by picking these 3 different models. So we have the model Max Planck, which is around 4.3, which is on the lower end. CSM typically falls in the mid, and even climate sensitivity of CSM2 is always in the middle of the bunch. And HAGEM is always very sensitive. And we picked these 3, and also the models picked have good resolution, spatial resolution, and the kind of data we need for doing the calculations. We evaluate this model with a whole bunch of data sets. These are the kind of data sets we use for soil moisture. For example, NAR is the soil moisture grid data, which is available, and the NAR data for precipitation, 2-meter temperature, and maximum temperature. Stage 4 for basically it's a radar output for very high hourly precipitation data sets. So these are the kind of things we evaluate our model with and try to understand what the model biases are. So when we do the analysis, we try to produce things like this. I mean, assess the performance of models using this. For example, temperature, we are looking at 2-meter air temperature, wet bulb temperature, wet bulb globe, and globe temperatures at 2, 5, 10, 50, and 100 years. So we are trying to see how often does an event occur in once in 2 years, once in 5 years, once in 10 years, 50 years, 100 years, for now and in the future. So that's kind of a risk calculation that we do. How is the risk from a particular event from temperature, precipitation, drought, wildfire, inland flooding, coastal flooding change? The frequency and the intensity are changing with time. So this is our kind of a matrix of doing these things, and we try to do this as often that the data permits us to do. But we can make the plots like most of the data is available every 1 hour with the 4 kilometers, and every 3 hours with both the 4 kilometers and the 12 kilometer data, ADA 1 and version 1. So we can look at the differences, which is PRISM is a kind of an observational data set, what we did with the ERA 5, which is a reanalysis data set with the WRF, and what is the differences. So you kind of understand the bias for the cool days, the warm days, the cool nights and warm nights. So we kind of do this for a very detailed analysis of this, and there are papers in preparation that we published before that do that. One of the things we do is kind of trying to translate it for application. So this is a application in the sense that Comet, which is a power utility here, is interested in seeing how the number of heating days and the number of cooling days actually change with the future. I don't want to go into great amount of detail here. This is just for from all the simulations we did, we are just looking at northern part of Illinois, and we see that number of heating days, the number of days you need to heat, actually decreases as you go into mid-century, and the number of cooling days, the number of days you actually start cooling, increases in most of the region covered by this domain. So other thing that we find that is very useful for trying to understand impacts and assessment, impact assessment, is the correlation between all the variables. So if you do a statistical downscale, you don't get this time correlation between the variables. The temperature at a particular time and the precipitation at a particular time and the relative humidity in a dynamically downscale model are all predicted by the model at the given time. So they are all affect each other, and they're all heavily correlated. This is important, for example, if you're looking at grid and power planning and things like that, because the models there are looking at correlated effects like temperature, wind, and the irradiance, and changing over a 5-day period. Like you get a lot of cloud and a lot of rain and very high temperature. So these are all happening at the same time. So you have to build scenarios based on that. So this downscale data we produce is very useful for doing those kinds of calculations. So the people we work here have generated statistical information for extreme events using that, and develop a probabilistic grid event scenario analysis. This is then used to understand what the power expansion and planning people are inform the planning and grid offices and grid development office and other people. So this is a lot of work going on there. The other place where we found it interesting is that people who are using building design are actually interested in time series of data of dry bulb temperature, relative humidity, and all these things that are listed here, about 13 variables that they use for designing a building, and in terms of how much heating should be there, how much cooling should be there, and how the building withstands various wind fields and all. So we have provided that kind of data for one of our team members has produced this thing. And these are interesting applications. So I mentioned that idea of risk analysis. Risk analysis. So the idea here is that weather and climate event, physical and social, economic, and exposure, they all affect risk. So most of our work we do is actually focus on weather and climate events. It's on the hazards end, but you need to couple it with the vulnerability and exposure to actually estimate a risk. But I'm going to focus mostly on the hazards here. So I talked about uncertainty analysis. We did only 3 model simulations, and essentially we have 6-member ensemble by mid-century. So how are we going to do uncertainty analysis with them? What we do is that we take the annual maximum of a given variable, like say temperature or whatever, for each grid point, and then resample that to produce a 500-member ensemble, and use that to calculate a range of possibilities by mid-century and end of the century. So if you compare, this is, in our opinion, this is better than averaging them or doing any weighted averages, because this actually resamples the data that we produce. And if you look at the PDF, the combined PDF actually is much better than just using the HADGEM. For example, HADGEM always behaves very different from other models in parts of the country. And this kind of normalizes that to a same behavior, if you may. So the idea here is shown here. So you have this model scenario. This shows for wind speed. You have this model scenario, you resample, build a PDF, and then it gives you a return period for over, this is 500 times with resample. So we can calculate this over a 500 events and build this uncertainty envelope for a 50th. If you want to use the 50th median, you go with 50th percentile value in this, go ahead and use that. But here is the 95th, here is the 5th. So if you're doing any decision making used on that, this is the kind of thing we hope people will be using. We have done drought projections for an entire continental US, and uses a method called VPD, vapor pressure deficit. It is at 12 kilometers available all over the US. It's also looking at the frequency. What is the frequency? What is the potential of once in a 2-year, once in a 5-year, once in a 10, 25, 50 years as you go along the y-axis. And it shows the percentile as you go along the x-axis, what is the possibility of a drop. So if you look at all the way to the bottom on the 95th percentile, that has a small chance of happening. But you see that the entire Midwest and most of the places in the Southwest that we expect droughts to occur can happen at the same time. And unfortunately, this map also correlates very well, overlaps with fire hazards, wildfire risk hazard that we have calculated from a different project. And it seems like the potential for both of them happening at the same time could be a challenge to people who are looking at long-term planning, resilience, and other issues related to climate change. So we expand this to, the idea is that not just downscale the climate, but take it down to impacts, right? We are looking at impact. So this is for flood risk. We use a model called WRF Hydro around 200 meters, and we have done tons of calculations. For doing this calculation, we do correct the precipitation as shown here. Basically, it's not a new method. It's you have a pot with points over threshold. You pick a threshold and points over that. We only correct the higher threshold values so that they kind of match. And then we use these values for running the WRF Hydro simulations around 200 meters. We have now completed these calculations for the entire US, entire CONUS, and they are available. For example, the results from that will show, for example, if you're looking at stream flow, this is the kind of data you can get. You can look at pick a particular river and then say, what is a once in a 2-year flow, 5-year, 10-year, 25 and 50 year. We don't have confidence beyond 50 years because we only have smaller amount of data. Once we do the 20-year one, I think with the 4 kilometers, we may have a better confidence going up to 100 meters. So it shows you historic and the future, and it is very useful for this. So percentage change in a median 50-year flood. This shows for the Northeast, where we have first completed these calculations. It shows you how this is changing as you, we call it pooling depth. And also for all the major cities, we can do this. But as was pointed out earlier, this does not include any of the storm systems or the municipal water systems that is relevant to the city. So we may have to do new calculations for each of these cities with either using the calculations we have done before or maybe start new for these small regions. One of the things we are trying to do is apply data-driven AI methods for extracting information and developing surrogate models. That's one of the things we are hoping to do soon with that is each of this is about 60 years of simulations at 200 meters for now and in the mid-century. So about 20 years now, about 30 years for now and 30 years in the future. So that's about makes it around 60 years of work simulation. That's about close to a petabyte of data. We also look at coastal flooding, and this is a model called EarthCirc, and it has been used for coastal storm research. This is from a nor'easter, and it shows the potential for a once in a 50-year flood in this region mapped on a GIS map. And we have done a whole bunch of these things. You can also look at, for example, what is the potential for a once in a 1,000-year flood from a hurricane for something like the one that hit New York, and you can see what the storm level, the maximum water levels will be for a once in a 1,000-year flood. These are important for people who are working on some particular industries like nuclear energy. They are interested in once in a 1,000-year event and sort of once in a 50-year event. These calculations actually use a synthetic storm tracks. There are almost 500 storms that you simulate, in addition to the historical storms to these calculations. So winter storm tracks, which these are from WRF, 12 kilometers. We calculated how they look for now, mid-century and 21st century. And it kind of shows you, we can estimate how the flooding along the shore will change because of the change of winter storm track. I'm not going to show that now, but I'll just show you a quick summary of where the data is. This is called climate.anl.gov. You can go here and pretty much get a lot of the data sets that I've shown before. For example, this is wildfire risk data, and it shows you for each pixel is about 12 kilometers. We will update this with 4-kilometer data as soon as we get that. And this has a whole range of variables like floods, and floods are not there yet. We are working with FEMA to show how fine we can go with showing that data. So we have not yet figured out that. This is mostly for wildfire, wind, temperature, various kinds of temperature variables that you use, cooling days, warm, hot days, and things like that. You can pick a particular grid cell. This is around argon. and you can just look at, as I just described before, it creates a table for you, and you can look at it. You can also download the raw data, and it's just one variable. Again, here shows one variable. There are about 12, 13 variables. If you need raw data files, you can contact me or one of my team members. They will provide it. So this is the team. Jialio is one of the people who worked on the 12 kilometers. Chen Yang is doing a lot of the 4 kilometers. William is the coastal hydrologist. Sujan and Eugene have been doing inland hydrology, and Brandy is done the drought. Tom Wall is the PI for the Climate Project. And these are all the other people who have been working. Jeremy has been very influential in making the risk analysis plots that I showed before. And Zach and Don, what used to work, they still work with us. Gokhan is now kind of taken over the simulations for the 4 kilometers. And we are working on. So these are all the people who support us. And again, if you want to look at our publication, there probably are a few. About 15, 20, around 20, you can go there. And I think everybody can have access to these slides, and you can also see where the data is. I'll stop there.
Cool. Thanks much, Rao. Perfect timing. It's really like 25 on the dot. Ben, would you like to moderate the Q&A, or in the meantime, I can already tell both of you. So Geeta Prasad, who's from the Southeast Texas UIFL, so our UIFL, she had to go to faculty meeting, but she has a number of very good questions in the chat that I can let you read. And in the meantime, the audience can warm up and think about what other questions to ask. Ben, do you want to take over?
Yeah, well, I think that those are some great questions that Geeta asked. And so I think we could probably go ahead and start with those. So Rao and Matei, you can read the chat, certainly. Would either of you like to respond to this the first question that she asked about uncertainty and how to communicate that?
Yeah, there's 2 questions the way I see it there. One is, how do we in our own work characterize uncertainty? Certainly we're not trying to indicate that RCP 8.5 or SSP 8.5 is the path of the future, and the development of these scenarios, like it's mentioned in the question, has no actual uncertainty associated with it. And so for that reason, and that reason alone, we try to bracket our simulations with what is considered broadly to be maximum emission scenario, what is considered broadly, I think, best case scenario. It's really unlikely that 2.0 is going to be manifest by the end of the century. In terms of likelihood, it seems from what I've gathered, but different people have different opinions, that 6.0 is probably the direction that we're going. And so 8.5 and 4.5 sort of bracket that. So it's a bit implied in our approach. In addition to that, we do a lot of ensemble-based simulations, which wasn't communicated very well in my discussion. And of course, some of that is smoothed out, and so you can't get an actual result. But tweaking the model simulation by changing the initial time by a month or 2 months actually does result in a simulated change that is indicative of the model variability, the internal variability of the model. And so accounting for that is important. You always, as a modeler, and I'm sure Rao will agree with me here, there's a multitude of different ensemble types of simulations that you can do. And so at some point you have to reach a decision on what you think the model is based on broad knowledge, the broad knowledge base that the community has developed. What are some of the most important attributes that you need to be considering? So sensitivity to initial conditions is one. Sensitivity, as we've communicated, to global climate model forcing, in addition to RCP pathway, is another one. Depending on the actual case study, if you're looking at precipitation, which I didn't discuss here, sensitivity to microphysics is really, really important. Anyway, those are just some general thoughts on the subject. As far as communicating this to stakeholders, part of our collaborative group, Lloyd Trenish over at IBM Research, that's one of his key areas of expertise, and I see him logged on here. I don't know if he's listening, but he's an expert in this domain, among other things, and he can definitely provide more insight into how we appropriately communicate this uncertainty to those that are making decisions, because that's a very important consideration. Lloyd, would you be able to jump on for a second? Sorry for putting you on the spot.
Lloyd, we don't hear you though.
Yeah.
Something is off with the mic.
Yeah. Yeah. There's audio, but it's garbled, so it does seem like it's a mic issue.
Should I go before you fix the mic?
Yeah, Rao, why don't you take over and then we'll pass
Yeah.
it back to Lloyd.
Yeah, so this is a basic fundamental issue for how to communicate with the stakeholder, even very educated stakeholders. Right now, we are working with FEMA on how to communicate flood, change in flood, once in a 50-year flood from now to mid-century. And it has been going on for 4 months or more. And the problem here is that if you show something at a 200-meter resolution, how it will change in the future, they have their flood maps and we have our flood maps. How does this overlap and how detailed should you go? So, and what is uncertainty on that? So this is non-trivial. Especially when you're communicating to a stakeholder, climate uncertainty, as Matei just said, there are so many variables. How do you explain to somebody who just wants to use the data to make a decision that there is internal variability, there is more risk, this variability, that variability. So it's a hard thing, but each of the people, like the stakeholder we talk to, they have a comfort zone where they understand what the uncertainty is and how they want to be represented, right? So, for example, if you're looking at a once in a 50-year event or like the frequency and intensity and the duration of a particular event, they are comfortable using the median value of all the distribution we are creating. Some people say, let me do the 95 percentile or 5 percentile. It depends on this particular stakeholder. But presenting this on a website like I showed, Glimmer, to a general audience is absolutely nuts. I have no idea. We have been trying to figure out how does somebody click on something and it gives you a value, and then it says this is uncertainty on that. And if it looks like the uncertainty is bigger than whatever the change, it will freak people out saying this is almost garbage, right? So where do we say that this is a representation of uncertainty and various things? But we know 98% sure that it is going to change. So this is the challenge here. I have no clear. We are trying to work, especially through the website and working with the stakeholders and how to represent it. And I'm sure of all the for RCP 8.5 to 4.5 for mid-century, there is no big difference. They are about the same. So I wouldn't worry too much about whether RCP, but end of the century, there's a lot more difference. Things like internal variability, if we go 30 years in the future, probably not a big deal. Again, so there are issues here, but I think one of the things we need to figure out is working with stakeholders is what is the best way to represent this uncertainty. We know there is uncertainty, but still that convey the information that such a way that this data is still useful for you. You can still go ahead and make use of this data. There is uncertainty here, just like every other engineering decision you make. Here is the data, here is uncertainty. It's not like every other engineering decision, but this is how you should be able to use it. So that's where I am right now.
Great, thanks, Rao. And Lloyd, sorry that we've had that audio issue, but Lloyd has put some thoughts in the chat here. And so maybe we can allow people to follow up with Lloyd based on those comments afterwards, so as not to suffer through audio troubleshooting. Great, thank you both for your answer on that. So Geeta has other questions, but let me pause for a second and ask if anyone else has questions. You either raise your hand or just go ahead and unmute. Well, I have a general question before you get back to Geeta, which is, these are both fantastic talks, and just a wealth of experience and opportunity to make use of existing methods and existing inventories for the urban IFL. given that we heard two different perspectives, is there any effort underway, or is there any useful way to think about comparing across these approaches? Either in the traditional sense, right, like what do the predictions look like relative to each other? But perhaps also even conceptually, right? Like what kinds of information do we get? What kinds of uncertainties? What kinds of questions can we ask with these two different takes on downscaling for an urban IFL?
So the national, there is a effort going on, mainly led by folks at DOE, that are trying to compare different downscaling methods, right? It's not this particular methods, like all the statistical, dynamic, all the stuff. So we just had a workshop in November in Berkeley, process of writing the report. I think the expectation is that a follow-on, there will be more workshops, as you can expect, and hopefully we'll come with the idea is that if you look at the National Climate Assessment 5, they only use statistical downscaling. There's the ESDM and LOCA. And we all know that there are problems using LOCA and ESDM, especially for Southeast, and there are hurricanes, they don't have hurricanes, and things like that. Anyway, so is it better to use the dynamic downscaling products? There are several groups trying to do that, including the, so Cordex experiment, for example. So we are trying to compare all of them probably and come up with some kind of recommendation. The idea is to get NCA 6 to use dynamic downscaling right now, and not just to stick to statistical downscaling.
Yeah, I would take a step back, Ben, and say that I think Rao and I are in complete agreement. Rao's talk was much more broader in the sense that he introduced the spectrum of approaches. And I think that the spectrum of approaches, it's useful to understand because each approach has advantages and disadvantages. Statistical downscaling is very useful if you don't have high performance computing capability. It's simple in a computational sense, it's easier to implement, and it produces a result that is relatively quick compared to some of the simulations that his group, Rao's group has done and my group has done. That's not to say that there's no room for dynamical downscaling. There certainly is, but you're limited by this computational constraint. If you're okay with this computational constraint, then there's significant advantages of the sort of dynamical, physically based modeling that we do, because it's not just about the process outcomes. We have a delta T of whatever, or we have a change in precipitation of whatever. It's about the processes, and it's highlighting how these processes lead to these outcomes. And that's really what promotes further understanding. Statistical models are limited in that sense. So there's ways to perhaps, and of course there's opportunities for AI as well, because our physical understanding is limited. I'll give you a perfect example. So not this winter, but last winter, it was the third of 3 La Niñas in a row. La Niña statistically is correlated with very dry winters for the Southwest. That's our statistical understanding. Our physical understanding is very conceptually based. We have a good understanding in a conceptual sense, but that's about it. That's as far as it goes. So what actually happened last year? We had one of the wettest and snowiest winters on record for the entire Southwest. Why weren't we able to predict that, right? Well, the answer is easy. It's because our physical understanding is very limited. And so for that sort of an approach, statistical approaches, for that sort of dilemma, statistical approaches are not very insightful because they don't provide the process-based understanding that allows us to get to these simulated outcomes. So I would argue that there's room for both, and that these two camps probably should be talking a lot more than they are, just like historically the global climate model folks have not talked to the regional climate model folks very much, and that there's advantages to both. There's a comment here about internal variability. I would argue, yes, internal variability is very important. You look at 30-year timescales like the shift in PDO cycles and how this manifests and interacts with ENSO and other modes of natural variability. In my simulations, we don't account for that because we're not yet conducting 100-year simulations. We're doing simulations at 10 years, maybe 20 years, and that's about it. So that's sort of a messy answer to your question. There's opportunities for both to better engage, right? There's advantages to both approaches.
Great, thank you. I see that Krista put a question in the chat that I think builds well off of Lloyd's comments. Asking if there's specific attention to the information decision makers need that is relevant to the topics they are focused or concerned about. And how might their concerns influence the models and research plan you do? Because I say it builds on Lloyd's. I think Lloyd gave a great general view on how you think about stakeholder information needs. And I read Krista's question as saying, well, specific to these IFLs, right? Is there a plan for how to integrate such concerns or focus areas into how we think about doing our projections?
For the CROCUS, we actually have stakeholders engagement is kind of central to what we are doing, because our science questions are based on our stakeholders, essentially the community partners in Chicago area, who have identified specific concerns for their neighborhoods that are related to some potentially we work with them to frame them in terms of climate change issues. So like local flooding or heating events and things like that. So which seem general in a sense, but I think people are more interested in very neighborhood scale issues. So how do I translate that's why we are driving the models that we do. 4 kilometers looked fine enough for me, but it's once you listen to the problems people are expressing, it's not fine enough. So how do I get to a hydraulic model that looks at the city, that has all the infrastructure of the city, where the city itself doesn't know where the pipes are? So that's a challenge. That one of the challenges, if you kind of simply put here for our problem, for even just heating the very warm days, we have to understand a little bit more about the physics of the urban canyons. So we are doing a field study to improve the urban canyon representation in a model like this, and also building street scale models and other things that address. So the science we are doing is directly influenced by stakeholders.
I don't have much to add. It's central to our work. I would say probably the most critical aspect for us, the WRF simulations that we're doing are down to 1 kilometer grid spacing, and the specific neighborhoods that desire, in this case, they don't care about the mechanisms and processes, they care about the desired outcomes. What's the delta T, right? What's the change in air quality or whatever? And it's specific for a particular neighborhood. So there's a scale disparity there that we're still struggling with a little bit. I think we have a path moving forward, but again, it's not something that is probably scalable. I mean, we can't conduct 100-meter resolution simulations for all of Arizona. That's not possible. But hence the need to work with individual neighborhoods. We can do that for individual neighborhoods.
Great, thank you. I think so, and Matei already mentioned Gita's question about the role of natural variability. So I think that's been addressed. Unless you want to comment on that, Rao, in the chat, we didn't talk about Gita and how you're thinking about natural variability and the bias correction. So I guess it's a very specific technical question related to the natural variability.
Yeah, I mean, so we have looked at this so-called internal variability, or I think close to that. So we have done a whole bunch of simulations. We have looked at, so when you look at a regional climate model, internal variability plays somewhat differently than in a global model. In a global model, you can see internal variability lasting 30 years. In a regional model, the simulations we have done, after 2 years, you really don't see much differences in the model projections. So the variability in the model decreases, especially if you actually do nudging. The variability dies in 6 months. There is no variability after 6 months. So it kind of settles. This model still settle pretty quickly into, even if you take a city like Boston, and we looked at a lot of these cities, it's kind of settles down quickly. I don't think it's a huge issue for regional climate modeling. We have run model every day, starting on a different day in December, and saw what happens. We have run 20, 30 member ensembles. But it's kind of different from global. If you ask me why, that is an interesting question, I would say. It is just that. But as you go into 4 kilometers, 2 kilometers, 1 kilometers, again, the variability is going to increase. And we need to look at the question of how various other things start affecting this internal variable.
Yeah, if I can jump on that. So the global model is not constrained. It's constrained by basic, sun-earth geometry. That's the constraint. For a regional climate model, it is constrained. So if you're focused on a seasonal simulation, you're going to see sensitivity to initial conditions. But Rao's right. If you're looking at multi-year simulations, the imposed constraint on the regional climate model will limit that drift significantly compared to a GCM where there's no constraint. The constraint is just sun goes up, sun goes down. That's it. And then the internal variability of the Earth system itself, which plays a very important role.
Great, thank you.
I had a question on land use, if I can jump in. Matt, you mentioned kind of like, modeling what's going to happen in the future for future Arizona, right? And that's a similar question is for Rao, thinking about these impacts on the ground. They're all going to be affected by how the cities, the areas are going to change, urbanization and so forth. I was curious for the two labs. I know Southeast Texas is doing some work on that, and I was just curious what approach your two labs are taking for predicting what land use is going to look like in the next 50 years or so.
We're currently using EPA data. We're using ICLUS version 2 data as of this point in time. So we're not developing those land use scenarios ourselves, in large part because Arizona's development is not, just like any other state or locale in the country, is not independent of issues elsewhere. There's not a complete disconnect. It doesn't happen in a vacuum. And so issues like migration have to be taken into account. Yes, there's people coming from outside the country to Arizona, but there's also a lot of internal flow into Arizona. And so we rely on EPA to conduct those very complex data set developments. This is widely available for everybody. They're now up to, I think, ICLUS version 2. And there are additional data sets as well. I think ICLUS version 2 is based, I want to say, on census, on the 2020 census, but I'm not 100% sure. But there's a multitude of different data sets out there that characterize population migration. The reason why we use ICLUS is because it's directly translatable to our land surface model and the way this is characterized in terms of our WRF runs.
Yeah, I think it's an interesting question. If you're doing RCP 8.5, where there are no mitigation strategies implemented, basically living as we live, I think it's much easier. If you do 4.5, there is an IPCC scenario which says what the changes we can expect in this region or globally. So you have to kind of match those two things to make sure that you are not double counting some of these things. And it's a interesting it's a challenge, but I haven't thought about that much. But yeah, sometimes I wake up to this. I mean, how are we going to match all these things, right? Because the downscaling is scenario based already. So what is how does your scenario match with that scenario? Maybe better doing these calculations off of RCP 8.5 because that assumes very no mitigation.
And to be clear, the ICLUS data sets, the urban expansion data sets are consistent with the IPCC world.
Yeah.
Right.
Yeah.
So it's difficult for us.
Okay, so that's good. That's maybe useful. Yeah.
Great, thank you both. All right, we just got a few minutes left. Does anybody want to get in another question before we call it an afternoon? All right. Well, this is great. Thank you both so much for those presentations. I think there are a lot of questions, and I'm sure there'll be more questions to come. And that's exactly what these seminars are for, right? Getting more exchange across the urban IFLs. And I know, speaking from the BSEC perspective, we're going to be thinking about this a lot as we develop our own strategies, and we'll be back in touch. So with that, again, thank you for everyone for attending today. Our next quarterly seminar is going to be on air quality. The CETEX and BSEC teams will be presenting then. And we look forward to seeing you all there and also have a lot more exchange between now and then.
Thank you.
Thanks,
Thanks.
everyone.
Bye.
Bye.